Much, Rock, and thank you to the entire awards committee, the entire SIGCOMM community. It's really my honor and privilege to be standing here in front of you today with this presentation. I have obsessed over this presentation a bit, as Rock mentioned, so I'm really looking forward to giving it. The title does reflect a rather profound technical journey that we've been on as a community. I think it has a reflection on a much less interesting, much less profound personal journey that I've been on, that I come back to at the end of this talk. I think it hopefully goes without saying that the material in this talk reflects the work of literally hundreds of the most talented and kind colleagues you can imagine. The magnitude of my own contributions to this work are substantially less than the magnitude of my good fortune in having worked with these people. So let me start with a bit of history with respect to the journey that we've been on the internet. I think you could start arbitrarily far back, but let me start in 1960, where there was this was before the internet, before the ARPANET. And I'll start with a quote from a gentleman named J.C.R. Licklider that I find truly inspirational. So I'm going to read it to you all. It seems reasonable to envision for a time 10 or 15 years hence, a thinking center that will incorporate the functions of present-day libraries, together with anticipated advances in information storage and retrieval. The picture readily enlarges itself into a network of such centers, connected to one another by wideband communication lines, and to individual users by leased wire services. In such a system, the speed of the computers would be balanced, and the cost of the gigantic memories and the sophisticated programs would be divided by the number of users. I find this quote stunning and inspiring with respect to the power of our collective imagination. Again, this is 1960, before many people were thinking about such things. And I would say that 60 years later, we've achieved a lot of what this quote puts forth, but we're not quite done yet. J.C.R. Licklider didn't stop with such quotes. He actually, the following year, 2 years later, was the first director of the ARPA IPTO, which laid the groundwork for the programs that would launch the ARPANET in 1969. And here is the apocryphal drawing on the back of the napkin that showed the topology of the first 4 nodes on the internet in ARPANET in 1969, the direct precursor to today's internet. 51 years later, we've gone from 4 nodes to 20 billion connected devices to the internet and 4 billion users. Approximately half of the world's population is on the internet, and that number is rapidly increasing. So a factor of 5 billion growth over a 50-year period is truly stunning. And I think that we in this community can take legitimate pride in our contributions to this journey. The internet truly, I think, represents a revolution. It is one of humanity's greatest achievements across time. It is the basis today of all human communication at any distance. It is the ultimate repository of human knowledge. And it is the basis for all planetary scale software services. Today, we're seeing that increasingly, it is the basis for all sensing and actuation of our physical world. And 50 years in, I think it's fair to say that we're just getting started. What can we imagine for the next 50, 60 years? At the same time, I think 50 years in, we are at an inflection point. And paradoxically, it may be that the underlying principles that enabled this revolution, this true revolution, may need to be revisited to allow us to take the internet to the next level. So what I'm going to be arguing in this talk and presenting to you in this talk is that the enablers of exponential growth that have gotten us through the last 50 years across the internet, but in neighboring domains like computer architecture, storage, memory, the enablers of this exponential growth have effectively stalled or come to a dramatic slowdown. This is at the same time that societal infrastructure demand continues to rise exponentially, in fact, accelerate. So we're facing a very interesting situation where the enablers of exponential growth are slowing or stopping, while the demand for the infrastructure is growing ever more rapidly. So putting these two trends together, we have a substantial challenge. And I believe that we have a once-in-a-generation opportunity to redefine what the basic model of computing is to enable us to sustain the necessary exponential growth to take on society's computational storage and communication needs. I believe that just as the past 50 years have shown, the network must and will enable sustained exponential growth in effective compute and storage capacity. Computing, storage, and networking are deeply intertwined. But we're going to have a really exciting opportunity in that the conventional wisdom that we've developed over the past 15, 20 years, depending on how you look at things, is breaking down. We're going to need to develop, in this generation, new conventional wisdom. We are on this manifest journey where we continuously conquer the previously impossible through tides of innovation, but we're at a transition point from one point in this journey to another. I'm going to present to you one taxonomy of the 50-year journey that we've been on, split across multiple epochs of time. I'll argue that we are just entering the 5th epoch of time, and some substantial transitions are going to need to take place, not least of which are we're going to need new programming models and new networking stacks to basically meet the evolving productivity and computing needs of our distributed systems. This will require, again, among many other things, a move from software-defined networking to software-defined infrastructure, really bringing together, finally, compute, storage, and networking in an intertwined manner. Okay, so continuing on the theme of history, let me present to you a taxonomy of 5 epochs of distributed computing. Each of these epochs, they have fuzzy beginnings and fuzzy endings, as all historical epochs do. Let's say that we start roughly around 1970 with both the birth of the internet and, interestingly, about the point in which Moore's law took off for computer architecture improvements in performance. We'll see that connect back later. So Epoch 1 consisted of applications like FTP, email, and Telnet. At this point, I also mark in each epoch the interaction time among computers. At this point, interaction time was on the order of 100 milliseconds. We had low bandwidth links, high latency networks, and again, there was rare pairwise interactions between expensive computers. Epoch 2 started approximately, let's say, 1984 or 1985 by one marking with the birth of RPC, the remote procedure call, and client-server computing. Fast, certainly for the time, local area networks. Interaction times maybe dropped to about 10 milliseconds. Networks grew to 10 megabits per second in speed. And we started, through things like RPC, sharing resources between multiple computers near synchronously. Epoch 3 saw the rise of HTTP in the web, 3-tier services, and massively parallel processing. 100 megabits to gigabit per second networks were commonplace. And we got to a point where complex applications no longer fit on a single server, and we had to scale out across multiple servers. Epoch 4, we saw, this is, let's say, around the year 2000, Moore's law hit its first wall, where after, let's say, 30 years of sustained exponential growth in the performance of individual processors, we no longer had any more performance improvements for single threads. So we basically hit a per core performance plateau. We saw the rise of web search and planet scale services, social networking, 10 gigabit per second networks were becoming commonplace. And we saw infrastructure scaling out across lands. So let's say data center scale services for storage, for data analytics, and many more. I'll argue that we are today at about the tail end of Epoch 4 and entering Epoch 5, where we're seeing actually perf per TCO for individual processors actually plateauing. We're seeing the rise of machine learning and the rise of data-centric computing. We're seeing interaction time among servers, let's say, and for the networks that support them, dropping to about 10 microseconds. 200 gigabit per second networks are starting to come out. And I believe in Epoch 5, we will see terabit per second networks. Specialized accelerators are becoming more and more commonplace, starting with TPUs, GPUs, and smart NICs. But I think that we're going to see an increasing number of these over time. It's interesting to look at what happens at a higher level with respect to the type of connectivity that we're delivering in these various epochs. Again, I'll provide the taxonomy as follows. In Epoch 1, we were interested in connecting people to computers. In Epoch 2, we got into the business of connecting computers to computers with local area networks and a remote procedure call. Epoch 3, the connectivity at the network level shifted to connecting services to one another and increasingly people in near real time to static data. Epoch 4, the networks played a role in increasing fraction of people-to-people communication, whether through social networks, through your cell phone or otherwise, but also people to interactive results. Right? There was not a static serving of content, but substantial complex code could run and return very interesting, rich results to people. In Epoch 5, I think we're going to be increasingly connecting people to insights with the rise of machine learning and data-centric computing. Integrating across these 5 epochs, I think it's also interesting to note that shifting from one epoch to another, we see a 10x increase in bandwidth and a 1/10 reduction in latency or interaction rate among the computers. And perhaps it is this relatively substantial shift over a 10 or 15-year period that allows the rise of the next epoch. What we see is that these epochs are marked by shifting, making the imaginable at the beginning of an epoch routine, but then finally, and maybe as importantly, making the impossible imaginable. I've heard a story that JCR Licklider obsessed in Epoch 1, around Epoch 1, about being able to echo keystrokes at the rate of 100 millisecond interaction times to remote computers to maintain interactivity. It seemed somewhere between hard and impossible, and yet we made it happen. If you consider where we were at the end of Epoch 3, at the beginning of Epoch 4, the notion of being able to run services across hundreds, thousands, tens of thousands of individual servers, tightly connected across a local area network, and having them scale out was imaginable, but perhaps very, very hard. Today, 15, perhaps 20 years later, it's now routine. So now that we've made the very, very difficult routine, what's the next rate of innovation, the next tide of innovation that we will take on in Epoch 5? Okay, so now let me shift to some modern day implications of the shifts in these epochs. And I'll argue that this march forward has been done in the context of building balanced distributed systems, with the network, as always, playing a critical role. So as I've argued, the network is just one component in any distributed computation, with others, in particular compute and storage, playing very, very important roles. In running your distributed computation, you have to think carefully about system balance. In other words, how much I/O are you going to have? How much networking are you going to have? How much compute are you going to have for your computation? And building that balance is critical, because if you build an unbalanced system, some resource that you happen to need at a particular point in time, compute, storage, and networking, is going to be scarce. And that's going to limit the value of your computation. On the other hand, if you build an unbalanced system, some other resource is going to sit idle, which is going to increase your cost. I'll put this in the context of Amdahl's lesser known law, developed again in the late 1960s, perhaps by coincidence, where you need 1 megabit per second of I/O for every 1 megahertz of computation in parallel or distributed computing. While this is a rule of thumb rather than a law of nature, it's actually held up remarkably well over a 50-year duration. Let me put this all into concrete context. Do these balanced systems really matter? And in fact, they do, in taking on some of the most challenging problems that we face. If you don't build balanced systems, you can dramatically limit the efficiency of your infrastructure. We took on some work for actually a contest, an annual contest called GraySort. At the time that we did this, about 10 years ago, the question was, how fast could you sort 100 terabytes of data? In about 2009, 2010, the world record holder was Yahoo, and they were able to sort 100 terabytes of data in 173 minutes, which was truly impressive for the time. But if you broke this down and looked at the configuration that they used, they ran this 100 terabyte sort across 3,452 servers. And then the rate per server works out to be 2.8 megabytes per second. If you want to put this in networking terms, about 20 megabits per second of throughput per server, which certainly for 2010 was not something that in the end looks impressive. Right? So now you have this large scale distributed system at substantial cost, 3,452 servers, but the throughput that you were delivering was rather limited. So we took on the question, how quickly could we do the sort on a much more limited university budget? Basically, could we put together a small scale cluster that could beat the results by being much more efficient and building a balanced system across disk, across compute, and across network to do so? It turned out to be much harder than we anticipated, but after a bit of work, we were able to beat the world record at the time. So we were able to sort the 100 terabytes in 107 minutes on 52 servers. And if you then look at the rate per server, that's 300 megabytes per second, or about a factor of 100x efficiency improvement relative to the previous record holder. So this argues again for the importance of balanced systems and the ability to actually improve the performance of your systems, not by building different hardware, but by composing your system differently. Now, interestingly, when we did the calculation, this 300 megabytes per second worked out to be about 25% of the roof line. What I mean by that is that while we did quite well, and I'm certainly proud of the work that the team did, we actually left a factor of 4 on the table. Now, I'll share that when I raised this with the students who did all the work on this program, they said, no way, it was way too hard to get where we were at, and there's no way with the tools that we have and the time that we have that we can get this remaining factor of 4. So again, all of this goes hand in hand. One of the challenges that the Yahoo team and others had at the time was that they actually didn't have the network bandwidth at the scale of 3,452 servers to be able to support a balanced system across disk, across compute, and across networking. So some of the other work that we were doing in parallel to this was investigating what it might take to build non-blocking topologies for the data center to enable the balanced systems that we needed for ultimate system efficiency. We started with thinking about topology and the basic approach, and that led to our work on fat trees and closed topologies for large-scale data center networks. We next looked at problems of virtualization, how we could have multiple tenants, perhaps in a cloud environment, running isolated across the network at scale. We found that existing techniques for balancing flow communication across these switches would lead to hotspots, especially given any variation in the size of the flows. So we looked at dynamically mapping flows to paths in near real time, but based on detecting the larger flows, the elephants, and being able to rebalance just that subset. And finally, we considered what it would take, given stability in communication patterns, to actually make the network even more efficient, more cost-effective by leveraging optical interconnects, especially higher up in the topology. The observation here is that actually most of the cost of your data center network comes from the optical connectivity between switches at any length, and converting between electrical signals to optical signals and then back to electrical is a substantial portion of the cost. Hence, could we do all optical switching at one region of the network to save on cost? So the implications of this work, as we looked at what it would take to scale out the network across the data center and then eventually across the wide area, was that the protocols that we had to build the internet didn't necessarily translate directly to the data center environment. So I think it's instructive to look at sort of the basics for networking. And this would be a slide that I might include in all of the network courses that I had the privilege of teaching over the years. What are the fundamental tenets of networking? I think it starts with best effort. So no guarantees about whether or when data will arrive. This actually made it very easy to join the internet and enabled that factor of 5 billion growth that we've really enjoyed over the past 50 years. Another tenet is soft state. That is, the state that we maintain within network elements are useful for efficiency, but not required for correct operation. What this means is that you can rebuild the necessary state to be able to carry out your function through pairwise exchange of messages with your peers. And of course, protocols are fully decentralized, right? Whether it's BGP, OSPF, ISIS, TCP, IP, DNS, or others. And what this once again means is that we have the ability to not rely on any central entity to control the evolution or growth of the internet, once again fueling its exponential growth rate. But what this leaves us with is individual end hosts managing the global network by constantly constructing, reconstructing, and then deconstructing global state through carefully constructed probes. The resulting protocols are beautiful, and actually some of the main reason that I was drawn to networking in the first place. On the other hand, for certain settings where you are running within a single autonomous system and where the highest levels of availability and the highest levels of predictability are required, where best effort might not be the rule, we then considered what it might take to leverage software-defined networking. And the question here was how to leverage at least logically centralized state within a single autonomous system to build out your network. And what I'll argue here simplistically, in the interest of time, is that the protocols that can leverage logically centralized state are going to be simpler and more efficient, easier to get right, easier to maintain over time. So you could imagine that in a distributed system, for you to exchange states, you're going to need order and login communication and order login steps to get to convergence. Whereas in a centralized system, again, in the best case, you're going to need order and communication and constant time to get to convergence. These are all idealized and all cartoons, but essentially it argues for simpler, perhaps faster protocols, if you are able to leverage centralized state. And in the interim, in the intervening 50 years, our peers have helped us develop deep understanding of scalable, fault-tolerant design for these logically centralized services. Now, it's not one answer or the other, as you're not going to go with full decentralization or full centralization. But the question is, can you turn the dial dynamically for what you need in a particular protocol deployment scenario? At Google, we've been able to apply these ideas to essentially all aspects of our network, starting with B4, our wide area network, Interconnect to Jupyter, our data center networking environment, Andromeda, which is our network virtualization stack, and Espresso, which is how we do peering with the public internet. Underlying all of these are the key considerations around availability, security, and isolation in our networks that allow us to move to these fifth epoch distributed systems that are now starting to rise. So briefly, I'll go through each of these. B4 is Google's software-defined WAN for our data centers. So interestingly, B4 is now bigger and growing faster than our public network. That is our connectivity to the rest of the internet, while growing very, very quickly, is not growing as fast as our computer-to-computer communication. Over the life of B4, it went from a non-business critical copy network that promised very little availability but cheap bandwidth to something that now actually has, depending on how you measure, as good or better availability than the public internet with, again, much more bandwidth. Andromeda is how we actually do network virtualization across our cloud infrastructure. And basically the idea here is leveraging software-defined networking to be able to program virtual machines with all the information they need to have the illusion of a dedicated network at the scale of tens, hundreds, or thousands even of VMs for their clusters. And we similarly applied the ideas originally started in B4 to Jupyter, our data center networks. And this has actually been across multiple generations. We started with standard data center network designs, but then grew them to the scale of, as of 2013, 1.3 petabits per second, again, leveraging commodity switches with remote control running the protocols. And finally, we were able to bring these ideas to actually the public internet with Espresso. And the idea here is that we can leverage the fact that we have actually many different points of presence across the internet, many places where we peer with the rest of the internet, to observe through randomized experiments the performance that particular clients get in particular regions based on what egress point we use in our network. So essentially imagine that we can keep track of the performance, reliability, latency that clients see based on how we forward packets to them across one of multiple paths. We analyze this information in near real time, so at the granularity of, let's say, tens of seconds, and then use this to feed back our forwarding information, again in real time, to pick the paths that are going to deliver the best quality of experience to our users. Again, this would not be possible without having this logically centralized state that can reprogram forwarding tables based on performance that's being observed across the internet, rather than what might be available at the purview of any single node. So where does this leave us with respect to software-defined networking and maybe more broadly the software-defined future? I think that there is a ton left to do. I think we've gotten to a place where the data plane for our networks is in pretty good shape. We are able to leverage high bandwidth communication at scale. The control plane, there's more work to do, but it is now at a place where it is reasonably robust and high performance. Network management, I think, remains a substantial problem and a substantial opportunity. So basically the way that we view it, and I think that many are looking at this problem, how do you transform higher level management states into a sequence of SLO compliance? What I mean is by basically SLO is the guarantees that the network is providing to its users. SLO compliant transformations that will take your network from one state to another. And I think there's been a lot of great work on network verification around central repositories, once again, leveraging the central state of ground truth to allow us to move from one state to another in this manner. I think we're going to increasingly see software-defined networking extend all the way to end hosts. This is already happening with network virtualization, but I think it's going to be extending with the rise of smart NICs into many other scenarios, as well as the rise of 5G, where we're going to have much more information about what the applications are experiencing. This will enable, I think, a new golden age in how we do congestion control, how we deliver isolation, and how we do routing virtualization policy. In the end, I think this is going to enable us to bring true networking as a service to companies and customers, essentially being able to compose the network they want in the shape they want with the performance characteristics that they want and availability requirements that they need to meet in near real time. But I think that in terms of tectonic shifts and big transition points, we're going to be making a leap from software-defined networking to software-defined infrastructure. In other words, the network is going to be playing a critical role in fundamentally how we build distributed systems. So now let me shift toward software-defined infrastructure and what this might mean. These thoughts are not fully formed, and I think that we are at the beginning of thinking about and understanding what this could look like. Let me start with the need that I hinted at early on. So this reflects in this particular graph 40 years of processor performance improvements. So this is normalized to 1.0, which is the performance of perhaps the computer architect's favorite architecture, the VAX 11780. So over the intervening 40 years, what we see is rather rapid increase in performance for a long period of time. But then as we went to the multi-core era, and today where we're at right now, the performance improvements in processors have substantially slowed to the point where we're now at, certainly when normalized for cost, single-digit performance improvements, single-digit percentage performance improvements on a yearly basis. All of this actually can be coupled with actually exploding demand for data. There are lots of ways to look at this. We have many internal measures. Here's one externally available measure. What this graph shows you is the amount of YouTube hours of video that are uploaded to Google every minute on an exponential y-axis over a 10-year period. That's the red curve that you see. At the same time, for that same 10-year period, you see the spec int rates for CPUs. Essentially what we're seeing is that at the same time that the performance of CPUs and our capability to process data is slowing substantially, the amount of data that we're having to ingest and process is growing even more rapidly. If you were to extend this curve out past 2016, actually the divergence would be larger. So as we move toward a place where we are increasingly again sensing and actuating the physical world, the amount of data that we're having to work with is just growing ever faster, right? So the exponential is increasing. And at the same time, we're hitting more and more fundamental limits in our ability to scale compute efficiently. So again, this divergence between demand for compute and the affordability of compute is rather striking. It becomes even more striking when you consider the rise of machine learning. So again, lots of ways to look at it, lots of ways to look at the explosion in demand for compute and the data that feeds it. This is, again, one public version of it for AlexNet to AlphaGo 0, based on an OpenAI study. Again, looking at it over a 6 or 7 year period with an exponential on the y-axis, what you see is a 300,000-fold increase in compute demand for running the various models that the community wishes to go after. And these are externally available. What you can imagine is that many companies are looking at even larger scale problems internally. So it's not hard to imagine that we're going to get to a place where machine learning compute demand is going to outpace general purpose compute demand, given the growth rate certainly that we're seeing today. So what are the implications of these trends? I believe that a single general purpose server architecture cannot generalize to all application needs because of huge variability in per service system balance. Okay, so what does this mean? It means that for the, let's say, the conventional wisdom that we've developed over the past 20 years or so, 15 or 20 years is, you could, because of the underlying performance improvements in the hardware architecture, leverage basically one general purpose design, deploy many tens of thousands of it, and use it as the basis for all of your compute with substantial average efficiency for all of them, okay? That one single general purpose architecture might not be perfect for any one application, or it might be perfect for only a small number of applications, but it would average out to be terrific across the board. That's no longer the case because the underlying performance improvements are slowing and stopping, and because we're seeing an explosion in the variety and heterogeneity of applications. What this means is that domain and application-specific accelerators are going to now proliferate. In the past, we could basically ignore 2x performance improvements. We could often ignore 10x performance improvements because the rate at which general purpose compute was improving was so fast that we couldn't basically figure out how to take advantage of a new accelerator fast enough from, let's say, a programming model perspective, or it wouldn't be widely available enough relative to general purpose compute where it would matter. That trend is going to end. And what that means is that given that we can't ignore the benefits of general purpose accelerators, we're going to see more of them, with GPUs and TPUs being just one example. Finally, what we're seeing is that individual hardware elements are getting ever larger to amortize fixed costs. So one of the ways that the community correctly is combating the trends that they're seeing is they're building ever larger CPUs, SSDs, GPUs, TPUs, DRAM modules and NICs, switches, and even new accelerators. But each individual one is so large that it cannot necessarily, it's not necessarily needed for all applications, tipping system balance in one direction or another. And then furthermore, it's actually even making reliability harder as these individual elements are becoming larger and larger. So what are the implications of these trends? As we're basically facing a slowdown in the underlying exponential growth of the capability of the hardware, we're seeing many, many opportunities, many hard opportunities arise at the beginning of Epoch 5. I believe that there is a greater than 10x opportunity in scale out efficiency of our distributed infrastructure in being able to leverage tightly coupled distributed computing and communication. So one way to look at it, again, as a cartoon is, we've been on the blue curve. We've built our distributed systems with loose coupling, and we've lived with relatively modest efficiency. So in other words, the performance scaling, while linear for our loosely coupled distributed systems, has gone out infinitely far. So we could scale out to 1,000, 10,000, 20,000, perhaps 50,000 servers and keep getting incremental wins. We're now at a point, though, now where doing so, given the slowing of the benefits from each individual server from generation to generation, where we probably have to revisit and look at tight coupling. Basically, what's it going to take to have much more efficiency on a per server basis, even if it means that you flatten out the curve much earlier because of inherent overheads that are introduced from tight coupling. I think the Triton Sword example is one that you could take away. Are you willing to take a 100x improvement, let's say, in efficiency, in exchange for perhaps limiting your scale, maximum scale? Okay, so that's one 10x opportunity. Another 10x opportunity is matching application balance to your virtual server or cluster composition. And this is where software-defined infrastructure can come into play. Essentially, imagine being able to extract the balance points for a particular distributed computation and being able to carve out an isolated subset of your compute, communication, accelerator, and storage infrastructure to match that balance point. I believe there's at least a 10x opportunity in efficiency there. And then finally, there's a greater than 10x opportunity in distributed systems developer productivity. Go back to the sort system that we built where we left a factor 4 on the table, and that's just one example. That's one example where we were able to do extreme amounts of performance work. Imagine that actually most developers don't necessarily have the expertise to be able to debug their large-scale distributed system. And that is only for a very small subset of these pieces of infrastructure that we do performance efficiency work across the community. So basically, what tooling can we provide? What programming models can we provide where distributed systems efficiency comes from, let's say, runtime, comes from a compiler rather than from human expertise? Combined across these three, I believe that there is a 1000x efficiency plus velocity roofline opportunity to sustain exponential growth. None of these are going to come easy. I'm not at all claiming that these are easy problems that any one team, any one company, any one group can take on. But I believe that it provides a framework for which we can continue the exponential growth of our infrastructure, working together as a community to go after each of these incrementally. All right, so let's look at what this looks like pragmatically. One observation is that while we figured out how to build ever larger clusters, 10,000, 20,000, 50,000 servers perhaps, it may be time to actually go back and think a little bit smaller. Shall we transition from clusters as the basis for computation to thinking about cliques for a subset of our computation? What you can imagine is the bandwidth that you have among your servers is in the end going to be limited by physical radius. So in a smaller scale setting, perhaps 100, perhaps 1,000 servers, can you imagine delivering 10x bandwidth, 40x lower latency to 200,000 cores today? And I believe the answer is yes, and you can do it economically. Can you then imagine having flexible compute, accelerator, flash, NVRAM, and DRAM pools to be able to compose them for individual computations. So one view of software-defined infrastructure in such a smaller scale clique world is being able to define virtual servers, right, as the basis for building distributed computation. Individual servers can be software-defined based on per job system requirements. And you can imagine composing them within a rack or smaller scale perhaps, but across a network in the end, across your pools of general purpose compute, across your accelerator, across your flash pool, your NVRAM pool, or your DRAM pool. Essentially, what do you need to hit the right system balance point to be able to run your computation most effectively? And then compose that out of the available resources within your clique, or perhaps your rack. So that's one basis for software-defined infrastructure. Now you can then generalize it and actually build your own dedicated cluster, if you will, virtual cluster for your distributed computation. And this will then take into account the more global for your computation system balance point, not based on necessarily any one server, because the individual virtual servers in your computation may have different requirements. But then how do you compose them together, again, with a network that can deliver the right level of predictability, such that we can, I think, critically move away from the defensive programming models that destroys efficiency today. Right? So necessarily, given the failure rates that we have in our network and the failure probabilities that we have in our network, we leave huge amounts of efficiency on the table as a result of forcing programmers to develop their code very, very defensively. So let's come back to the 5 epochs of distributed computing. This is the original view of it that I put on. But I think it's also instructive to look at how programming models have evolved over these epochs. So moving across the epochs, what we can see is that with the birth of the internet, FTP, email, telnet, there was no concurrency model in building a distributed system. Everything was sequential, and you put bytes on the wire. In Epoch 2, as we moved to RPC, concurrency wound up being event-driven as a convenience. Think of your classic select loop in building your client-server systems. With Epoch 3, you started having to think about concurrency more seriously. As we hit the I/O wall, we had to develop multi-threaded code for efficiency. In other words, once we accessed, let's say, local storage or perhaps even remote storage, we had to think about how we would put that one thread to sleep and then move to another thread such that we could get the right level of performance. Here in Epoch 4, as basically single core performance improvements slowed and stopped, right? We hit max single thread performance. We actually had to go to concurrency models, multi-threadedness for performance. We had to split computation across multiple threads and to be able to scale out sequentially within a server. We're seeing that people are increasingly thinking, how can I make this easier for my developers through declarative specifications? Finally, as we transition into Epoch 5, we're going to need a distributed runtime. Developers aren't going to be able to think about the system balance points on their own. And in fact, as they change the code, the system balance point might evolve. So I will argue that declarative specs are actually going to be required to manage the complexity of building tightly coupled distributed systems in Epoch 5. What you can see in moving from Epoch 1 to 2 to 3 to 4 to 5 is that we have increasing developer complexity. Right? Building applications maybe at the birth of the internet, at least in retrospect, is simple. But we've gotten increasing concurrency and increasing complexity and increasing performance and correctness problems as we move from no concurrency to the beginning of Epoch 5, where we have multi-server, multi-threaded concurrency that we have to deal with. I'll argue that today, very few can actually get the concurrency models with multi-threading right. Certainly if you account for correctness and very subtle bugs that get introduced, but especially if you account for the need for performance. I'll argue that as we go to Epoch 5, no one can actually manage the complexity of the concurrency model. And we're going to need the equivalent of an operating system and runtime to manage the distributed state. So very quickly, for time and as a case study, let me show you how many distributed applications are built today. This is how we scale out, for example, web search, but not just us. This applies to many, many different scalable services. Essentially what happens is that requests come into a coordinator. The state of the system is partitioned, statically partitioned across, let's say, 100, 1,000, 10,000 servers. And the coordinator then distributes the request to all 1,000, 10,000 servers, and asks for a partial response. Code gets run locally within each partition, going over the locally stored data, and then a snippet essentially is returned back to the coordinator, which joins across all of these snippets to compose an answer. This is a very powerful design pattern, and it's generalized to many different services. That's a big pro. But it actually limits how we can do distributed computation. There's no branching. There's a static partition of the data, basically defining a static balance point. And data is pre-replicated anywhere that it might be needed, because it requires careful per application tuning. And again, if your code or your needs change, it requires some of the best engineers in the world to consider how things would get repartitioned. In Epoch 5, to drive the efficiencies and the productivity from a developer perspective that we need to be able to move at the requisite speed, imagine being able to move from a very partitioned view of your data to a more global view of your data. Essentially, can code run where and when it needs to run without having to think statically about what the partition is? This is going to require, again, a distributed runtime. Can we have a declarative spec of your computation? Can we maintain dynamic runtime state and be able to perhaps replicate and move data as well as the code in response to current access patterns? So many open hard problems in the space. One of the things that I'll argue for is that actually to date, we have gotten away in the networking community without common benchmarks. And as we transition, I believe that this is going to have to change. So I would call on us to put together a common benchmarks that we can all use to track our progress. And I'm inspired by the quote from Patterson and Hennessy, for better or worse, benchmarks shape the field. We will absolutely need new programming models for the fifth epoch of distributed systems. I find it both interesting and scary that many are still performance and correctness debugging the distributed systems with 32x terms, get time of day, and printf, which is how I was debugging my distributed systems certainly 25 years ago. Rack scale disaggregation, clique scale disaggregation is an open hard problem. And I think the biggest aspect of it actually is how we manage fault and performance isolation. Basically, as we move beyond the boundary of a single box for the basics of server computation, how do you protect against individual failures, certainly from the perspective of the developer? And then finally, I think we're going to have to increasingly move beyond flows and connections to ensembles and services. We're going to have to think all the way up to the application level. Developers, the vast majority of developers, near 100% of them, do not care about or know about IP or TCP. The entry point for them is the remote procedure call, and even that might be too low level. So we in the networking community need to help. We need new primitives around application data units that are transferred among many endpoints. So technical conclusions of this talk. Exponential growth in the efficiency of distributed systems have transformed society. At the same time, the historical drivers for this exponential growth are slowing or stalling. At the same time that the demand for compute, storage, and networking continues to grow exponentially, if nothing else is actually accelerating. So we're left with a wonderful opportunity, actually, and I'll repeat, a once-in-a-generation opportunity, where the conventional wisdom that we've built up over decades is breaking down, and we're going to need to develop new paradigms for how we build, scale our distributed infrastructure. The networking community, I think, is incredibly fortunate to have this opportunity. So what community can look at its first act, bringing ubiquitous communication to the planet and enabling large-scale distributed systems that have truly transformed society? The second act is actually going to be as exciting, where we transition from general purpose hardware to drive the next 1000x improvement in scale and efficiency for our computation infrastructure. Okay, before concluding the thought, I thought I would share some closing thoughts more broadly, maybe mostly non-technically as well. So some idle perspectives from my own career. In no particular order necessarily. I'll start with the first. Pick a great advisor and team, then stay in school. When there's this asterisk that says, I assume you have intrinsic motivation. And this is, of course, mostly for the graduate students that might be in the audience. If you truly love computer science, I think that there is a huge benefit for staying in school. But maybe the underlying principle here is that people matter more than projects. So pick a great advisor, pick a great team, pick people that you would love to work with. But I'll say that your research may not change the world, but the discipline and rigor that you'll learn to bring structure to ambiguous problems and to communicate these trade-offs and design will benefit you for a lifetime. Next, I'll say follow first and last and lead from behind. Why I say this is that I see many people impatient to lead. They want to be the leader. They want to be the go-to person. But I'll say the number one prerequisites and the most important thing for being a great leader is actually being a great follower. Follower is almost considered a bad word, but I would say that for you to know how to lead, you have to know how to work well in a team. And as a leader, you should know that actually, this is why I say follow last, only lead when you must. And when you must, ideally lead from behind. In other words, your goal isn't to tell people what to do. Your goal is to ensure that the team that you're a part of is hugely productive and happy. And this comes to the next point I'd like to make, which is invest in people first. While we're all excited by the technical opportunities in front of us and the technical impact that we can make, certainly I am, I think that with very high probability, the legacy that we leave behind, the mark that we leave, is going to be defined much more by the impact, positive impact that we have on people, rather than our contributions to technology. So think about people first and take a chance on someone, would be my advice. In other words, basically, to whom can you reach out a hand and not think in terms of how can this person help my technical goals the most, but perhaps how much would this person benefit from working in this area? How much can I help this person? Persevere. I'll say that how you handle adversity is much more important than how you handle success. And that in the end is what's going to define you. And going back to the point on leading versus following, patience is absolutely a virtue. Nothing comes quickly. It takes a lot of time and effort. Finally, and most importantly for me, what I want to say is that kindness is the ultimate nobility. Don't underestimate the value that a kind word can have on someone. And conversely, don't underestimate how a small malice or a small microaggression can really take a toll on a colleague. Let me share a personal anecdote, one of many, many. As a graduate student, I had just had my sort of signature thesis work rejected for the third or fourth time. And I was feeling down at the time. I gave a talk on the work at a research retreat. Jim Gray was in the audience. And in the feedback session, Jim Gray said, called out my work and said, Amin, he outvisioned the visionaries. And it wasn't true. It wasn't true by far, but it was kind. And literally, though I don't think he knew it, that gave me the strength to carry forward. I was truly doubting whether or not I was cut out for graduate school. But it was that small kindness, among many others, that gave me the strength to continue and to finish, literally in that moment. So let me close this presentation on a personal note. I stand here before you all deeply humbled, but I stand here for at least two reasons. Secondarily, I think I am a reflection of the power of sustained exponential growth. I take it upon myself every day to try to get a little bit better along some dimension. But what I've learned and realized over the years is that that's not sufficient. In other words, if you were to look back 25 years and ask any colleague or even any friend, what are the chances that I would be standing in front of you under such circumstance? They would laugh, and they would laugh for a good reason. I'm a dreamer. I like to dream big, but never in my wildest dreams dared I have such ambition. So what I realized, actually, as I thought about this, is that this sort of self-serving, self-perpetuating, self-myth of me pulling myself up by my bootstraps through growth mentality is part of the answer, but it's actually not the primary answer. The primary reason I stand before you today is because of the kindness of others. And the list is incomplete and the list is long, but what I can say is that through active kindness of those who stood with me, stood behind me, and when I needed it most, literally stood in front of me, showing the path, or clearing the path. That's the primary reason that I stand here before you today. I've learned a lot from that, and while I know that I don't have the hope of necessarily repaying the kindness that I've received from those I've received it from, I do intend to pay it forward, and with sufficient time, my hope is that I can give almost as much as I've gotten. Thank you very much.